Good afternoon, everyone. So, am I audible to all of you at the back? Sure. So, I think you had a very strenuous session, some 4 days. So, this is going to be a very simple talk. Okay. So, this is on page rank. So, all of you would have used this. This is an algorithm. All of you would have used it, and you'd be using it every day unknowingly. Okay. So, let's just see what it is. So it's got to do with how search engines like Google work. So all of us know that Google has access to a whole lot of web pages, around 8 billion pages. Okay, and whenever you give some query, you get the results in very less time, right? In just less than a second also. You don't have to wait at all. Okay, so what is it that Google is doing for you in that time? Okay, how is it able to fetch you such accurate results, and how is it ranking the pages? Okay, so that is what the page rank algorithm is about. So for this you need some background on linear algebra and probability. So already last 2 days Manjunath sir had given some very good sessions on them. So I'm not going to assume any background as such. I'll cover whatever is needed for the algorithm in this talk itself. Okay, so feel free to stop at any point when something is not clear. Okay, so starting with linear algebra, something on vectors. So all of us know what vectors are, right? So you're just going to represent some numbers of some dimension. So an example is some features like how well can you sing, paint, play, and all that. Okay, so if I want to distinguish between a professional singer and amateur, the values will vary for the singing field. Okay, so these are just some examples of vectors, and so something called the norm. Okay, that tells you how. That tells you how, on an average, what is the length of the vector. Okay, that is given by norm, and the dot product is like to measure how similar two vectors are. Okay, so I think all of these things you would have learnt in your 12th standard itself. So I'm not telling more on these. So one thing is matrix multiplication. So in yesterday's talk, Manjunath sir had given some view of matrix multiplication. I want to give you some other view. So like how is this multiplication done? Okay, usually what you do is to get, like if you have to multiply two matrices A and B, to get the entry ij of the result, what do? You take row I of A and column j of B. Okay, and you take the dot product, right? That's how you normally do. So here is one alternate representation. Rather than doing a dot product in that way, there's another thing. So you can say if you want to multiply a matrix A and a column vector B. Okay, so how you do it is you take each of the columns of A, okay, and take a linear combination of them. Okay, so do you all understand what linear combinations are? Right? Does anybody have doubts on that? Is it a new term for anybody? Okay, I'm assuming everybody is clear since no one is responding. Okay, so yeah, so what do you do is in this B matrix in this B vector you have two entries, right? So you take 1 times the first column of A and 2 times the second column of A, and you sum them up to get the result. Okay, so that will be one of the columns, that is the column vector, that is the result. So you can view, if you have a matrix B, then you can do this operation for each column. Okay, is this clear to you all? Okay. So similarly, you can have a row-wise interpretation also. So if your first matrix A is a row, so your result is a combination of the rows of B. Okay, so that's how you get 1 times 2, 3 plus 2 times 4, 5. That is the result you get. Okay, so that is equivalent to doing that dot product that you have done. Okay, these are giving you the same results. Okay, so now, yeah, this is again eigenvalues and eigenvectors. So all of you know how to compute them, but just some intuition on exactly what these are. Okay, so consider an example. You have a vector So I'm representing each of you using two numbers, okay? How well you can do some public speaking and how well you are in your technical work or research, okay? So suppose at the moment, I can represent you with this vector x, okay? Now, there is some matrix which acts on this x. So this matrix you can think of maybe the summer school. Okay, you attend the summer school and after that there's some change happening to you. Ideally, there should be some change. Okay, so suppose something is going to happen to that vector. You're a transformed person, and in the best case, you are twice better in all these things: public speaking and research. Okay, so just see this for a minute. So initially, you had a vector. There's a matrix which acted on the vector, and it's the same vector, the same direction, but the magnitude has improved. Okay, the magnitude has changed. Okay, by a factor lambda. Right, so that is what these eigenvectors are about. So it is something special, right? Like when a matrix acts, you can go in any direction, but the very fact that you're getting the same direction with a changed magnitude, that's what makes an eigenvector special. Okay, so this lambda is the eigenvalue and x is the eigenvector. So how do you get these? That you all know, right? So you find this is the way: a minus lambda x is 0. So you need to solve this. Determinant a minus lambda a should be 0. So that is how you get the lambda. And once you have the lambdas, you get the x. Okay, you solve the system of equations to get x. Okay, there is some more interpretation about why this should happen, but I'm not going into those details now because it's just a 45 minutes talk. Okay, so is this clear about eigenvalues and eigenvectors? The intuition behind it. Okay, so now I'm just switching to an example in probability, which would be needed for understanding page rank. So assume that like I'm interested in studying about how people, what people do for a living, okay, what people do for a living or how they spend their time. So assume that I use some set of states to denote this information. Okay, so one is a student at CSA here, is a very hardworking student. Okay, so that is one. The second is an idle researcher who spends all his time sleeping and maybe a little amount of time doing some research. Okay, so and the third is somebody who is doing a job in some firm, okay, in some company or maybe some of the professors or anything. Okay, so for now think that there are just these three kinds of people in this world. Okay, so I'm denoting I'm denoting S as a student in CSA, I as the idle researcher, and J as somebody who's doing some job. So I'm interested to see how a student transforms to any of these cases, or either ways, okay, whether it's possible to move from one state to the other. Okay, so it's not, none of these things are permanent, right? Nobody is going to be a student always, or okay. So to denote this, I have some kind of a graph. Okay, so what this means is that, so say take this student. Okay, this is a node for a student, and so in CSA the placements are quite good. So most of them end up with a job. So with 0.9 probability, a student ends up working in some firm. Okay, and yeah, sometimes a student gets very much disillusioned and becomes an idle researcher, but that is very less. It's 0.1 probability. Okay, and seems like no student returns back to CSA, so there is no self loop here. Okay, so this is just a cooked up example. Okay, so now look at the person who's working at some job. Okay, he's very much settled with the job, so there's more chances that he remains there. So there's a 0.7 probability that he stays there. Okay, and sometimes he would feel that it would be helpful to do higher studies because he gets some promotion or something. So 0.2 probability he becomes a student in CSA. Okay, and again he gets disillusioned with probability 0.1 and becomes an idle researcher. Okay, so similarly you have some transitions for the idle researcher also. He's mostly idle, so it's 0.6 probability of staying there. Okay, and yeah, sometimes he suddenly gets interested and becomes a student, and sometimes he feels that he doesn't have money and he ends up applying for jobs. Okay, but these are very low probabilities. Okay, so this is just a simple example that I've taken. So this is a graph, as you can see, with probabilities. So another way to represent this is in terms of a transition matrix. Okay, it's the same information. It's an adjacency matrix actually. You all know about adjacency matrices, right? So what it says is that in each row, so take the first row. So if I'm a student, what is my probability of being a student, being an independent researcher, and landing up at a job? Okay, so that is the first row. Similarly, you have entries for each of the states. Okay, so is this clear what this matrix is? So all of you are fine, right? No doubts on this, right? Okay. So now let's just see what happens to a student. So I'm representing a student as a vector. So let's say there's a probability distribution that I'm interested in, that where is any person who enters the system, what is he going to be after some time steps? Okay. So for a student, his initial state is 1, right? He's a student. So 1, 0, 0 is his probability distribution. So is that clear to you all? Why I'm representing it in this way? Okay. So I want some response. Everybody is sleeping, it seems like. Okay. Fine. So pay attention because I'm going to ask you some question at the end of it, and maybe if you had listened, you can even attempt it. So, okay. So, right. So for a student, he starts off with 1, 0, 0. Okay. Now, after the system acts on him, this matrix H is going to act on him. So, after one time step, this is his new probability vector, right? So let's say maybe after 2 years of study, or 2 years of ME here. So, that time you are seeing what is the effect, okay?
What does this probability vector represent?
So, this probability vector is like saying, what is the, like, okay, with what probability will you be in each of these states at any given time? Okay, so at time step 0, this is a particular case for one person. Suppose it is 1, 0, 0. So that means he's a student. With probability 1, he's a student at CSA. Okay, so it's like you want to see where are your chances, like where will you end up eventually. Okay, that is what you want to study, and for that you want this probability vector. Okay, so after one transition, so this is what you get. Okay, so if you see that this multiplication, I already talked about it, right? So it is a row vector times the matrix. So when you do that, so here the entry is 1. So 1 times the first row. Okay, so you're getting exactly the same thing in the first row of this matrix. Okay, so that is P1. Now, again you can do one more transition after some time, and you get this vector. So keep doing this. Okay, so at every time there's some change. Are you seeing that? Right. So initially started with this 0.19, and afterwards there is some change here. Okay. Keep doing this, and it now looks like these numbers are going somewhere, right? Because from 0.9 it started tending towards 0.6 and so on. And these numbers also, it started changing towards 0.17, 0.18, like that. So finally it turns out that it reaches this vector. Okay, and after that, if you do one more transition, there is no change. Okay, you end up with the same vector. So the mathematical term for this is the system has converged. Okay, it converges towards this vector. Okay, so that is the case if you started off with a student, 1, 0, 0. Now, what happens if you started off with an idle researcher? For somebody who is an idle researcher, the vector is 0, 1, 0. Right? So one transition takes you here. You keep doing that, you end up with this number. Okay, so the interesting thing is whether you start off as a hardworking student in CSA or as an idle researcher or somebody with some job, finally these vectors, these numbers are the same. Okay, So are you all seeing that these numbers are exactly the same? So what this means is that after many time steps, after several years maybe, the probability that you become, that you land up with a job is the same, irrespective of where you started off with. Okay, and even similarly these numbers also. So this concept is called Markov Chain. Okay, this process that I just told you is an example of what is called Markov Chain. Okay, Manjunath sir yesterday just mentioned it briefly when telling about matrix multiplication. So turns out that this is a very important example for PageRank. Okay, this kind of processes, and these distribution that you get, these numbers, these are called steady state distributions. Okay, so there's a whole lot of theory about Markov chains and steady state distributions. So you can check it up later on. So I'll give you some references. So for the purpose of this talk, this is all you need to know about Markov chains. Okay, so now we are done with the basics, what is required. Let's go to what actually Google is doing. Okay, so up to here, is everyone with me? Like, do you have any questions? Okay. Nobody's sleeping, right? Okay, fine. Okay, so let us see how to devise an algorithm, okay, search engine algorithm. So before you do that, you need to understand what is the kind of behavior that any person who is surfing the web, how he behaves, what is the way in which he browses pages, okay. So one typical activity is this. A person starts off with some Google News site or something. He sees some offers and he sees a link to Flipkart pages and he goes there, does some transaction. Okay, so this is everything. He's starting from a root page and then following the links there. Okay, and then he's doing some set of activities. Then after all this, he feels like doing something else. So he jumps to some other web page, maybe to check some movie reviews, and then to Amazon. Okay, so this is the kind of activity. So the point here is that on one side you have this set of activities where you follow the links on a page. Okay, you follow the path shown by a page, and this is like a random jump. So you jump sometimes to some other pages. So all of us do this, right? You don't always follow the link structure. So given this is the activity of a surfer, how do you see which pages are important? Okay, so ideally you want to calculate some number, you want to associate some number with each web page, okay, and rank pages based on that. So one idea for seeing the importance of pages, okay, so it is analogous to some example that we see around us. Okay, so consider that there's a student who is applying for some PhD positions abroad maybe. Okay, so he gets recommendations from very reputed professors in some well-known institutes like IISc. Say one person is called Double Brain and Math Heavy and Excellent Writing. So all these people give him good recommendations. On the other hand, as a student who gets recommendations from reasonably well-known professors. Okay, so these guys are much better known. So the student has a better chances. Student A has better chances of cracking the admissions. So he gets a score 5 and the other student gets a score 1. Okay, so this is something that you can relate to, right? Like if you have some important people pushing you, then your importance also becomes more. Okay, so that is the same idea that is used in PageRank. So if there are some important pages linking, like suppose you have a web page and if you want to push it up, so if you have some other popular web pages having a link to your page, then there are more chances that your page gets some hits. Okay, so that is the idea, okay, in devising an algorithm. So is this clear to you all? Is it clear? Yes. Okay, fine. So, okay. So now let's take an example of some pages in the web. So let's say A, B and C, D are some 4 web pages which have links to each other. Okay, so this graph is the link structure. So from the web page A, we have links to B, C and D. Okay, and from B we have outgoing links to A and D. Okay, and so on. Okay, so this is the graph of links, and again you can write it as a matrix. Okay, so here, like compared to the previous example, I didn't have any weights. I don't have any weights now. In the previous case, I had some probabilities. So here, what I'll do is, to get these entries, I see the number of outgoing links from any node. Okay, so from, say, this node A, there are 3 outgoing links, right, to B, C and D. Okay, so then I say that from A to B, C and D, the weight is 1 by 3, 1 by 3, 1 by 3. Okay, it's 1 over the number of outgoing links. Okay, so similarly you can construct this matrix, and for the node C, there is a link only to A. So this entry becomes 1 and everything else is 0. Okay, so is it clear how we are constructing this matrix? Okay, fine. So okay, can you tell whether there is anything particular about H? Yeah, sum of the rows is 1. Okay, so this is called a row stochastic matrix where the sum of the entries is 1. Okay, so there's something about these kind of matrices which will turn out to be useful. Okay, so I'll come to that point later. Now again, like in the previous example, it is assumed that there's a probability vector. Okay, so Vt of A, so it is a probability of being at page A at some particular time. Okay, so yeah, this is a vector which sums to 1 because these are probabilities. Okay, so now, okay, so suppose initially you start with some probability. Okay, let's say how you compute this Vt of A. Okay, so at any time instant, what is the probability that you are in web page A? So how do you get that? So you'll see, like in the previous time instant, what is the probability that you were in B? Okay, and what is the probability of making a transition from B to A? Okay, so that is this Vt minus 1 HBA, and this also Vt minus 1A HAA. So what is the probability that you were at A itself in the previous time instant, and what is the probability of making a transition to A? Okay, and similarly you'll do it for C and D also. Okay, are these, is this clear to you all, how you get this? Are there any questions here? It's clear to all, right? Okay, so yeah, so in short you can write that Vt is Vt minus 1 times H. Okay, so what is the probability vector in the previous time instant times the matrix H. Okay, that's how you compute this. Okay, so we already mentioned that H is a row stochastic matrix. It's guaranteed to have an eigenvalue 1. So that is the important property that it has. So okay, so this will turn out to be useful in computing page rank. Okay, so again the same example you take. Initially, suppose the probability of being at any of these pages is 1 by 4. It's equal, right? Because you start off that way. You don't have any bias towards any particular page. Okay. Now after one time of following the linked structure, you get this vector V1. Okay. Now keep doing that. Okay. V2 is again the same way you compute this. And at the nth time instant, you have Vn minus 1h. Okay. And what you want to see is where does this converge. Like in the previous case, we had the 3 kinds of people who converge to one point, right? So similarly here also you want to see where does this vector finally converge. So that shows like how much, what is the probability of being at any of these pages, okay, in the long run over several time steps. So in short, what you want to do is you want to find a vector V such that VH, after doing a transition, you get back the same vector V. Okay, so this is guaranteed to happen because of this property. It's a row stochastic matrix. It's guaranteed to have an eigenvalue, and there's some more conditions which we'll come to. Okay, so how do you get this V? It is the left eigenvector of H. Okay, is this clear to you all? Okay, so somehow nobody is responding. Is it very boring, the talk? Okay, so you can interrupt if there are any questions. Okay, so yeah, fine. So this is how you compute the vector V. So it turns out that that is like giving you an idea of the importance of a page, because that is a probability with which you will hit that page in the long run. Okay. Now this matrix looked very good, like the rows sum to 1 and yeah, some other conditions, those were all satisfied. So let us just see what those conditions are. So one is what we all saw, this row stochastic, and then there is a concept of irreducible Markov chains. So what it means is that from any page you can touch any other page. Okay, it's possible to reach any other page. So this doesn't mean that these entries cannot be zero. So it means that at some point in future it's possible to reach the other pages. Okay, so yeah. Okay, so now the other thing is this property called aperiodicity. So I'll tell you what periodic is. So if you have two nodes like this, x and y, two pages where x links to y and y links to x and nothing else. Okay, so at one time instant, if you are at x, at the next time instant you will be at y for sure, nothing else. Okay, so these things are called, these kind of chains are called periodic chains. You don't want that kind of a structure because you want to be able to reach every other place. So that's why you want aperiodic Markov chains. Okay. So now look at this example. So here there's a problem, right? Because this matrix D, this page D doesn't have any outgoing links. Okay. So one row of this matrix becomes 0. So immediately it's violating the property, the row stochastic, that is being violated. So how do you handle it? So these kind of pages will be very common, right? Like it's not that always you have every page links to every other page. You sometimes you won't even have any outgoing links, right? Okay, so what do you do when you encounter these kind of pages? Okay, so any suggestions? Does anyone have ideas what you should do with this row? Okay. Okay, with a probability 1. Okay, it is in some sense that, yeah, it is, yeah, somebody else said something? Self loops, is it? Okay, there are many ways you can go about it, but one thing is it should make some, there should be some intuition about why you are doing that. Okay, so there you can do one thing, like you can add 1/4 probabilities to every other web page. Okay, so what are you saying by doing this? Like it means that even though you hit a dead end D, after that your activity is not stopping there. Okay, and then you can start a new activity by going to any of the other web pages. So just because it doesn't have an outgoing link, it doesn't mean that the surfer stops at D always. Okay, so that's why you have this 1/4 for every other page. Now, okay, so somebody said you can add a self loop itself to D. So that means that you're always staying at D and further there is no more activity. So that doesn't seem to model the behavior very properly. Right? If you're doing that, then something else you have to do. Okay, because you have to model the user behavior properly. Okay, so is this clear to you all? Okay, so now what you can do is with this new matrix, you can perform the same operations. This is now it is satisfying all those properties, and it's a Markov chain. You can find the steady state distribution. Okay, is this clear to you all? So yeah. Okay. So now. So if you remember initially in the behavior of the random surfer, there were two kinds, right? So one is when he follows the link structure and the other is when he does some random jumps. Okay, so you need to account for that also, that we have not taken care of till now. Okay, so what you do is you introduce one more matrix where every page is equally likely to be visited. Okay, so you assume that the surfer follows this link structure most of the time, and sometimes he makes a jump. Okay, so yeah, so for that you form a new matrix G, which is alpha S plus 1 minus alpha times B, where alpha is tunable, like however you want you can set it. Now you repeat the same kind of things that you did for the previous matrix here also, like get the eigenvector corresponding to eigenvalue 1. Okay, so in short the algorithm is this. So you get the pages which contain the query words, and then you use this page rank, this vector, to determine the order in which you should display the pages. Okay, so an example is this: suppose you searched for cars in India. Okay, so Maruti has a higher, ends up getting a higher score because it is more relevant. So that should ideally go on top. Okay, so this is about the algorithm, and yeah, there possibly many other extensions also to it, but in the simplest form, this is what is PageRank. Okay, so yeah, so these are some of the references that I've used. So Gilbertstein is one of the best books in linear algebra, and for Markov chains, you can see this Sheldon Ross. And PageRank, there is a book on the PageRank algorithm itself. Okay, so these are, you can check these up at a later point. Yeah, so I guess that's about it. Okay, okay. So you understood this part, right? Like how you get this matrix. So this is with the linked structure. You're following the linked structure. Now when you make a random jump, so initially we saw that after some activity is done, sometimes you make a jump to some other web pages. So for that, what you do is, to model that kind of behavior, you say that the probability of visiting any other web page is 1 by n, where n is a number of web pages. Here it is 4. In this example, it says 4. Okay, so then you have this matrix, full of 1 by n's, and then you say, what you do is you give some weightage for this matrix, and the remaining 1 minus that weightage for B. Okay, so that you want to still ensure that these rows sum to 1, and these are valid probabilities. Okay, so that's where you have this matrix. Yeah. This one? Okay. Yeah. So you understood this thing, right? Vn is Vn minus 1 times h. At every time instant, you are computing this new vector. So you want this to converge somewhere. You want a vector such that even after you do one transition, you get back the same vector. Okay, so you want something like this: Vh is equal to 1 times V. Okay, because it doesn't change after that point. So this, you are assuming that there is an eigenvalue 1 here. So that is guaranteed to happen because this is a row stochastic matrix. So question for you all: can you prove that a row stochastic matrix is guaranteed to have an eigenvalue 1? Okay. So if you do this, I guess you get some goodies. Okay.
So it take a probability, outgoing arrows. Every time it will be the probability will always sum up to 1. So that the probability for the edges, outgoing edges will be given, so that it will be added, and it will be always 1.
Yeah, but then how is it guaranteed that you can find some vector like this? What is that vector? Can you have some intuitions on why this is guaranteed to happen? So what you said is right, the idea is correct, but then that doesn't still prove that there is a vector V that exists.
We are using Markov chains, and Markov chains obviously after some time it will start repeating and it will stop, maybe it will stop.
Yeah, that is the definition of this, but how do you prove that? That's the thing. Yeah, so as per this, like whatever this algorithm is there, it's not fast. Like computing the eigenvalues itself is going to take time, eigenvectors. So there are some optimizations that have been proposed. So something more you need to do. So some extensions have to be done.
How is the value of alpha?
Yeah, alpha is actually a tunable value. So it's like you have to play around with these values. So in machine learning, there's this thing called cross validation. So it just means that you have to try out different values of alpha and see whatever you get best. So like based on some feedback, you have to set it. Yeah, there is no real formula for setting the value of alpha. Like it's just by some intuition you have to set it. Yeah. Okay. Can you write whatever you're? Can you come to the board and then?
Finding an eigenvalue, you
Ah.
need the determinant of A minus lambda into the identity matrix to be 0. Determinant. And so here the sum of these row is equal to 1.
Right.
Is equal to 1. So when you know A minus lambda I, and when lambda is 1, you are subtracting 1 from the diagonal element.
Right.
And so since it is it is a row stochastic matrix, then the sum of each row is 1. So now when you've done A minus lambda I, you get A matrix minus 1 in the diagonal element. So it will necessarily, the determinant will be 0. You can do the determinant to 0.
So, no, if you do this, okay, it's in the diagonals, if you subtract a 1, you are saying the determinant is guaranteed to be 0. So how are you saying that? Sum of rows is, sum of, yeah. Okay, so in this case, actually, we are, it's a left eigen vector. So actually, we are working with H transpose. Okay, so actually, it's the columns, right? The columns are going to sum to 1. Yeah, so this basically the same thing, whatever you said. Yeah, so you can, even a simpler way of saying that is, if you take the vector 1, 1, 1, 1, so where all the values are 1, if you multiply it with this matrix, you're going to get the same thing back because these are probabilities, right? Okay. So, yeah. So, yeah.
You are able to assume that there are no periodic, like there are no cycles. But in real life, there can be cycles in phases.
Yeah, so correct. So something else you need to do to handle that kind of scenario. So it doesn't allow that kind of a thing. Or even if it does cycle, it shouldn't be that is the only place where it cycles. You can go to some other place. In the other example that I gave you, sorry, it's after this. Yeah, here this was the only possible thing, right? So this kind of a thing is not allowed. Like at every time period when you can say for sure that you're hitting this, okay, that is not allowed. That's just what it means. Okay. Yeah.
Does it consider the weight of the link every time? If it's the link is coming from important page or from a diagonal, does it consider that part?
Yeah. So actually, that is what you're trying to find here. So you're trying to find the importance of pages recursively. Okay.
If it doesn't take care of that part, then it is easy to pull it. Like I can upload some page and some random 1,000 websites along with that point to that page.
Yeah, but those websites should also have some important things linking to it, right?
That's what I asked. Like,
Yeah, so this is the way it has been designed is considering the importance of pages. Otherwise, you can just see the number of clicks or the number of incoming links to that page, and it's just a deterministic thing. Okay, but here you need to compute the importance of pages also, and that depends on other pages linking to it. Okay, so because you have this kind of a thing, right? Like VH equals 1 times V. So that is where you're considering this importance of the pages. Okay. Somebody else had a question?
Okay, if there are no questions, we'll break now for Yeah, we'll be back at 4. Yeah, so we'll break for a break. So the students